Okay, Organic Chemistry 2341. We're going to continue with Chapter 10, Radical Reactions. Okay, so what we learned about before in the last chapter is, number one, how the process works with its initiation step, propagation step, and termination step. And then we also learned that there's a reactivity ratio based on the type of carbon we have doing the reaction. All right, let's continue that with some hydrohalogenations of alkenes and look at the reactivity process we see here. Okay, so the first thing we want to look at is that when we did addition of HBr across an alkene, we got the Markovnikov product, meaning that the hydrogen went on the terminal or the least substituted, so the one that had the more hydrogens on it got the hydrogen, and we ended up with the bromine on the more substituted carbon. Okay, and we called that rule Markovnikov's rule here. Okay, so that in that we had the electrophile, in this case the hydrogen, added to the carbon with the most hydrogens. Okay, so if we do that same reaction, but instead of doing it with just HBr, we add a peroxide so that we're generating radicals in the system right here, we actually see we get primarily the opposite product. We have hydration on the secondary carbon, and the bromine goes on the primary carbon. Okay, this works specifically with HBr. HCl and HI are very endothermic and require a lot more heat. Okay, oops. Okay, so let's look at the mechanism of the process here. So whenever we use peroxide, the first step is the generation of that peroxide radical, or the alkoxy radical here. Then that radical reacts with HBr to produce an alcohol plus the bromine radical. Okay, so the hydrogen goes on to the alkoxy radical, liberating the bromine radical available to us. Now we have a choice here that once we have the bromine radical come in, we have it attack at either the primary or the secondary halide. If we have it attack that primary part of the alkene here, we will generate a primary bromine with a radical in the secondary position. Okay. Okay, if we generate the radical in the secondary position, that can abstract a hydrogen from HBr to add a carbon-hydrogen bond to that secondary position in a propagation step, regenerating an equivalent of bromine radical, which then can come back into and react with another alkene. Okay, so that creates a termination step for our process to create a primary alkyl halide. Okay. So one of the other termination steps available to us here is that we can have two bromine radicals combined to form bromine themselves. Well, luckily, bromine can actually do a homolytic cleavage and reintroduce itself into the reaction here. The other thing that can happen is a bromine can actually terminate that secondary to give us the dibromo product, or we can actually have two of the secondary radicals combined to form an extended hydrocarbon chain. Okay, so that means that the process that generates the best product for us is the propagation of this material here. Now, remember, in propagation step, the slow step is just generating the first radical, and then the reaction of all the radical processes beyond that are very, very quickly. And we don't get to these termination steps until the concentration of those things increases. So these termination steps tend to be low yielding, and the propagation steps tend to be the highest yielding, meaning we get the primary alkyl bromide as our primary product. Okay, so let's talk a little bit about why it seems to break the Markovnikov's rule. Okay, now we often call it, because the hydrogen ends up on the more substituted carbon, we say it's anti-Markovnikov's addition. But that's not true, because the true Markovnikov's rule states that the electrophile adds to the carbon with the most hydrogens. In this case, bromine radical is the electrophile. They're technically, the bromine radical is adding to the carbon with the most hydrogens on it, which is that primary carbon. And then that secondary halide, the secondary radical, is actually abstracting the hydrogen from the other system. So technically it is following Markovnikov's rule. Without the peroxide, the addition of the cation, if we don't use the peroxide, we can actually form that cation intermediate. And so we have that carbocation that can rearrange. So therefore, in the absence of peroxides, we can actually get rearrangements of our products if it's possible to create a more stable cation. When we form the peroxides, when we use the radical system, we do not form a carbocation. If we do not form a cation, we do not have that carbocation rearrangement. Remember, radical reactions do not have rearrangements. Carbocation reactions do have rearrangements. Okay, so let's talk a little bit about the stereochemistry. Just like with carbocations here, we're going through an intermediate where we have an sp2 hybridized carbon with a 2p orbital. In the case of the carbocation, the 2p orbital is empty and carries a positive charge. In the case of a radical, that 2p orbital has a single electron in it. Okay, so what that means is if we start with a compound that has a stereocenter, we will generate a mixture of, when it comes with attack to the top and attack to the bottom, a one-to-one mixture of R and S. Therefore, we become a racemic mixture of enantiomers. If we start out with a chiral alkane and we generate that radical on that chiral center, we will have attack at the top or bottom equally one-to-one. So we will have a one-to-one mixture of that R and S, which gives us a racemic mixture. If we start out with an alkene, we will also end up with that radical forming that intermediate. We'll get a one-to-one mixture of the top and bottom, and we'll end up with a racemic mixture of enantiomers, okay? Now, that only works if the chiral carbon is the one generating the radical, okay? So if the chiral carbon is the one generating radical, we're going to get attack at the top and bottom, giving us a racemic mixture. If that carbon is one removed, where it is not forming that radical or not forming a carbocation, then that stereocenter is retained, okay? It's only the carbon that forms the radical that generates the mixture of R and S products. Okay, so now we've done a primary versus secondary versus tertiary and looking at the stability there. Well, just like we had when we had double bonds in conjugation, we actually have a stability of having a radical next to a double bond. And the reason it has is because we can draw a Lewis dot resonance structure to show us that it is stabilized because it can move back and forth. Okay, so in this case here, we have a double bond with a generation of a primary radical. That primary radical could go a total of 1 to 3, go to that carbon back and forth. So we actually end up with a resonance hybrid of partial radical on one carbon and then a partial radical in the 2 carbons over. So it can go back and forth, back and forth. This also happens when you generate a radical that is the carbon right next to a benzene ring, because the double bonds in the benzene ring can also stabilize that radical, generating a stabilized system. Now, that being said, that means that the allylic and the benzylic radicals are more stable than a tertiary radical because of this resonance stability, okay? So let's revise our stability of radicals here. So our most stable here is going to be our benzylic and our allylic radicals because they're stabilized by the double bond, sharing that radical nature across multiple atoms. Then we have our tertiary, secondary, and primary, which are next. The vinyl and methyl are least stable. This is because we have a radical on an sp2 hybridized carbon. All the rest of them are an sp2 hybridized with an empty p orbital. And so this is actually using one of those p's as well. And so our methyl radical is least stabilized here, okay? So think about that as the more stable it is, the faster it's formed. The faster it's formed, the more it propagates, and therefore we get a greater yield, okay? So the high rates of formation of these benzylic and allylic radicals, as well as cations, explains why these can be problematic, because we'll get this movement of the reactive site. So for example, if we had a system where we generated a radical here. And so we have a difference between a secondary radical and this tertiary radical here. So what's going to happen is instead of reacting at this site here, we're going to get more of the product at our tertiary radical site because it's more stable. Same thing here is if we generate it as a secondary radical here versus this primary radical, the secondary radical is actually more stable and we're going to get more products here. But it doesn't mean that those other resonance contributors don't exist. They do exist, and when they do, we can get reaction at that site. Okay, so how can that help us with this halogenation at those benzylic or allylic carbons? Okay, well, we can look at that as a way of helping us, because if we take our halide here with some heat, the heat will, of course, generate that radical here, and we get very selective bromination at that single carbon right off of the benzene. It's not going to do other hydrocarbon areas. It will selectively create a halogen at that benzylic position right here. Now, we can also use a different reagent that helps us specifically use a reactivity site at that allylic site. Instead of adding bromine across a double bond, we can actually take it one carbon away from the double bond and maintain the double bond while brominating if we use this radical process. And the reason it works is that we get to form that allylic radical that generates our final product. So in the case of cyclohexene right here, if we just added bromine to it without a radical former, what would happen is we get addition of bromine across that double bond. However, if we use radical generating reaction conditions, either a peroxide, heat, or light, and this specific source of bromine called N-bromosuccinimide, or NBS, we can actually form that allylic radical, which would be here or here, and therefore we can generate an allylic bromination here while maintaining our double bond. Okay, so let's look at the mechanism of how that works. As with all of our radical reactions, we start with the initiation of a radical here. So that radical of the peroxide will generate a radical of the succinimide here, plus the bromine radical. That bromine radical can then abstract a hydrogen from the allylic position of the cyclohexene, generating an allylic radical, which then can move back and forth, back and forth, back and forth. Then that allylic radical will then be terminated, that allylic radical will then react with bromine to generate our product here, which is our brominated product, plus regenerating another equivalent of the bromine radical, which then of course goes into this initiation step. And therefore what we can do is end up going back and forth until we end up with our termination steps that allows us to yield a bromination allylic to a double bond without brominating that double bond. So it's all about having that allylic radical. Instead of doing an addition across the double bond, we're doing a substitution in the allylic position. Okay, so let's talk about a little bit of the Regio Chemistry we end up with that. If we have a possibility of forming a primary or a secondary right here, we'll end up with a mixture of products. And the reason we end up with a mixture of products is because we end up with forming some of the radical here as the allylic position, some of the radical here as the allylic position. So we have the possibility of getting a 3 addition or a 1 addition for the system. Notice when we do this, we end up with an internal double bond. Here we have a terminal double bond, and therefore we have an interesting competition between the more substituted and less substituted alkene plus the bromination effect. So whenever we have the possibility of this butene forming that radical going back and forth, we actually will end up with a mixture of products. Okay, so how can we use these in a much more controlled fashion to give us the products we want? Well, the number one way these are used industrially is actually to make polymers and doing polymerizations. Okay. In this case, let me define polymer. Polymer is a very large molecule, typically made up of the same repeat unit. That same repeat unit is called a monomer. So that's one mer or one unit. And then a polymer is multi-units or multiple units. And therefore, by definition, a polymerization is the joining of many units together to make a multi-unit system, or a monomers to make a polymer system. One of the really common ways to do this is to use vinyl monomers, or use a double bond with some other group attached to it. Z can be a variety of different things. But the key here is by using a radical polymerization, what we can do is we can turn those alkenes into alkanes, and it does it in a very specific and a very regular way. Okay, so let's look at this system here. Again, Z can be a number of different things that we have here, and so that when we make our material react to form a radical, what will end up is our radical is going to be on the more substituted side, and then our radical is always going to attack our least substituted side, and then that generates a radical and then does this. What that means is we're going to join the units together in a regular fashion. Okay, so let's look at that radical polymerization as far as its steps: initiation, propagation, and termination. Okay, so the most common thing that happens here is we get what we call a head-to-tail polymerization. So most of the time we use some kind of peroxide as an initiator. Once that peroxide reacts with a single monomer unit, it generates an attack at this least substituted position, generating our radical at our more substituted position. Then that more substituted radical can react with that to generate another radical. And so this is the propagation step, where this can just continue to react with alkene, 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 generating multiple units in the middle here. And then at the end, we end up with our termination step, where our concentration of our alkoxy radical here is high enough that it can terminate this step, and therefore we end up with no radical generation form. So our termination step is always a radical-radical coupling. Okay, so these are three examples of polymerizations that are used industrially here. Again, Z can be a variety of different things. In this case, we're using chlorine right here. And so we get this head-to-tail reaction of reaction here with reaction here. And so we see this regular, the double bonds were in these locations initially, and now they're used to create this long chain system. And PVC, as you may know, is commonly used in plumbing pipes. It's PVC, polyvinyl chloride. It's commonly used in that. We can also do it as a radical addition across an isoprene. So instead of getting a 1,2 addition like we would get across here, we end up with a 1,4 addition across this, giving us a retained double bond, but we get a very regular system in which we always get a Z conformation, and this extends out into a great thing. This is actually, isoprene is naturally found in rubber trees, and that's actually used to make natural rubber in the system. And it makes it very high molecular weight and high, it has really cool stretchy property. Another thing, again, Z can be a lot of different things. If we use it as benzene, we can create that chain that's very regular, and this makes a very tough polymer called polystyrene. You may know it. It's some of the clear packaging, as well as inexpensive polystyrene foam is used as well. So most of these industrial polymers are done with a radical polymerization. And so radical chemistry has a great deal of use in industrial chemistry, and it can be used because you can initiate with heat, light, or peroxides as your system.